So we're going to talk a little bit about programming and programming best practices. So I wanted to share a little case study first. This is Lockheed Martin SR-71, which is the first real use of titanium. It's a relatively old platform, but can anybody tell me how Russia's stealth programs go? Any hints? No. I don't think they have one. I don't think they're able to successfully do stealth. So we're going to start off with a little bit of review on motion instructions. So we have our speed settings, and the speed settings correlate to different motion types. So we have the motion types here. This is at the beginning of the line call. So you have your J, your L, C, and circular arc. And this gives you the range of what speeds you can put in. So you can do a percent of max speed, seconds, millimeters per second, centimeters per minute, inches per minute, milliseconds, and degrees per second. And the square brackets, anybody know the difference between square brackets and round brackets? No, it's a hot topic. Inclusion or not. So if it's a square bracket, you include that number. If it's a round bracket, it's excluding the final number. When it comes to doing when you're talking about cycle times and stuff, I tell a lot of my students to program in seconds, because you don't necessarily need to have the most rapid accelerations just because you can do 4,724 inches per minute doesn't mean you should, because force equals mass times acceleration, right? Newtonian physics. So when you're doing that, you induce a lot of force on your part or on your payload. So a lot of times we resort to just doing seconds, because that's what your cycle time, your performance metrics based on anyway. Termination types depend on your motion type. So we have our joint, linear, and circular, and we have our fine termination, which will end right on the final point, and the continuous termination interpolates a path or cuts the corner. So you end up losing some precision, but what you lose in precision, you gain in speed, because you don't come to a complete stop. So when we're looking at an exterior corner, is that a circle? No. Yeah? Stop. Okay. What if I do this? Is it a circle now? Yep. I'm gonna make you justify it if you keep saying that. That's a circle? I'm just like, oh, okay. Well, okay. So if I have this outside corner and then I cut this corner off, right, like a CNT, I cut that corner off. Is that a circle now? No. Okay. What if we cut these corners? Is that a circle? Stairs. Stairs? Okay. Still not a circle though. Or still not an arc, right? You know what an arc is for reference? Right? So that's still not it. What if we... Is that a circle? Nope. Okay. What if we cut the corners off and double the number of turns? Is that a circle? So it's a trick question, right? There's no right answer, but at some point this is going to get so fine that it's going to look like a circle, right? It's just like pixels on a computer screen. They're all squares, but eventually you get the fine enough resolution that it looks like an arc or it looks like a circle. So that's what CNT does. Instead of you having to go and plot infinite number of points between 2 points to give a circular arc, it cuts the corner for you and gives you a perfect arc every time, or a perfect circle. And another note about CNT, so if I have a part that comes out like this, if I have a fine termination point, if I'm starting here, let's say, and ending here, I can easily, with a fine termination, set a third point up here. And I'll go to my path to my first point, my path to my second point, and I don't have any interference or collision. But if I were to do a C&T with that point, a C&T of 0 might be something like this. And then a C&T of 10 might be something like this. And eventually, if I do a C&T of 100, I'm going to try to path right through that point. So you can't always use a continuous pathing, but there are ways to work around it. So one of the things you can do if you need to maintain a continuous path is you can have your start point and your finish point, and you can set a couple points out here and have those be C&Ts, or you can either pull this way up and have a big compensation, or you can have a couple C&Ts and these corners will sort of get cut like that. And this point is like what you would call a Bezier curve. It'll sort of pull everything that way, and then this point will pull everything that way and get you away from the collision. Any questions so far? So this is all about optimizing your path when you're in free air, when you're not laying a bead, right? So which termination type should I use? Depends on the criticality of the point. So if you're actually laying a bead, you have a highly critical point or set of points, so those should probably have a fine termination. And if you're returning to home or you're in guaranteed open airspace, you can do rapid motions with C&T terminations. Okay, so we're going to get into basic programming structure. Still no questions? So carpenters made buildings, the way programmers made programs. The first woodpecker would come along, would destroy all of civilization. And then Lazy said, journey of 1,000 miles must begin at the single step. Okay. So this is the industrial standard for industrial automation robotics, and it determines 5 different languages that are utilized by different companies. So you might have heard of ladder logic, or function block diagrams, or structured text, which is what the robots use. Our robots use structured text, which is what it means when you have those fields. So like you have your movement type, and you can have a J or a L or whatever, but that's really like it's like a field, right? So you can like highlight that field, and you can change from a predetermined set of choices, right? So that's what they call structured text. Modern best practices, well, this is for later on, but usually you have a sequential flow chart to do your states of your machine. So a state might be waiting for a command, or putting down a weld, or returning to home. Those might be all different states of the machine's in. And then you would use ladder logic to define a sequence of tasks within each state, and a structured text to define the functions that do the heavy lifting. So I racked my brain a little bit and came up with some elements of a program or some analogies. So one of them is building a house. So you have what's in your house. So you might need things like bricks or lumber, and how you're going to assemble those things, or how you're going to put them together is with a plan or your blueprints. In welding, you'll have your materials again, and then you have your procedure. And similarly, when you're writing a program, you have your data or your variables, and then your instructions or your code, which is how they work together, right? It's like your plan. Program structures usually have a heading comment. So this is in English or in the vernacular, something that's human readable is the point, right? Tell the programmer about the program, so when I boot up the program, I can read it instead of, because right now you all have a naming convention for your files, but it doesn't tell me what they do. So this tells the programmer when they go and open it what they're expecting it to do. So if you might put dates in there, you might put where you're at locationally, what you're attempting to do, what the job calls for, whatever the procedure is. And then a lot of times in other kinds of programming, you'll have data declarations which describe the data that the program is going to use. So this is like saying what materials you're going to use before you start assembling or welding your stuff. And then you have your executable statements, which come at the end or make up the majority of it. That's the body of your program. In programming, we have something called comments. Comments are written for people, by people. They're ignored by the computer. The computer doesn't read them. And the comments will describe the variables and the instructions in human readable form. So these are notes by the programmer to a future programmer or to themselves in a year or whatever. If you're doing an iterative process, then you might have multiple iterations of the same procedure trying to get things more efficient or better product or whatever. So that can be used for that, to log what you tried to do, because how do you know what you're going to do if you don't know what you've done? Comments can also be used in troubleshooting. So this is a different meaning of the word comment. If I have multiple lines and I'm crashing into something, I might put a comment in front of one of these lines, and it's not a human readable form, but it still keeps the computer from reading it. Since the computer is not reading it, then it gets skipped over, and we can find problematic parts of our code by doing that. Yeah, and the best part of doing a comment like that is that you're not deleting the whole line. So if that's not the problem line, if the problem line is further down, you can just come back and uncomment it, and you're back to your normal function without having to delete or add anything. All programming languages have some way to comment, but it can be called something else. In this case, we call it remarking. So in Fanuc language, a comment refers to a short text string that attaches to a register. It can be turned off and on for an entire program with one call in the menu. And these are useful for giving clues about what each line does. So this is a third type. So this is attached to the registers here. So this is register 1, register 1, register 3, register 101. And so when you have a position right now, it just looks like this, P1, or when you're turning a digital input on, it looks like this, or a digital output, or your laser. But if you turn comments on, then you can put a comment for each one of these registers. So you can name this your home position. You can name it the repair position. The digital input might be something like on our educational cell, we have the door that will open, and that's a digital input to the machine. And so you can have that read out that the door's open, and that's why it's preventing you from proceeding, because you need to close the door. Likewise with having a gripper, so a digital output could be used to open and close a gripper, and it actually gives a context, right? It gives a meaning, because this gives you no hints or no clues. And likewise with the laser. So to do that, to do a remark for the programmer in human readable language, do the inst key, which is one of the soft keys, miscellaneous remark, and this is wrong, it's not 250 characters, it's way less, something like, well, it depends, but I've seen it as little as 4 characters. But you can also do what they call a multi-language remark, and this will do a huge block of text, and you can write stories or jokes or whatever in there. To comment entire single lines, you do EDCMD remark, and that's one of these where you can That's not writing human readable text, but that's doing this thing for just a line. So you highlight the line first, and then you do that remark call at the bottom.